Oh, it's a real pleasure to be invited to give this 15th Athena lecture. Well, I think James has almost summarized my life for you, but the request here was not just a normal technical presentation, but to interweave it with a little bit about my journey. Towards a silent aircraft seemed appropriate because it's what I started off studying and it's what I went gap of about 20 years. So in some ways it's been a winding theme through my professional career. So I started by studying mathematics, and I graduated in 1973 with a BA in mathematics from Cambridge. And in mathematics I was really interested in applied maths. I really wanted to use the mathematics. And towards the end of my course, I studied areas around fluid mechanics and solid mechanics. And I was looking to see what I could do with fluid mechanics. And I found the answer in a summer job at the Royal Aircraft Establishment in Farnborough. And it was at the time when Concorde was starting to do its proving flights. And the noise that it was making was an issue. And in fact, it looked as if it might not be allowed to land in the US because of the noise the aircraft made on landing. And of course, Concorde was flying at a Mach number, 2.2 supersonically. So an aircraft that was flying at different speeds from a passenger aircraft ever before. And it had opened up whole questions about aircraft noise. A, it was a lot more important, but B, it was in a completely different parameter range from previous aircraft. And we genuinely didn't know, if you change things, whether it was going to make things better or worse. So here were some really great research questions where whole order one effects, sign of the change that would be produced, was just not known. And I thought it would be a great area in which to go into. It was really opening up. So I looked to see where it was good to do a PhD in aircraft noise, and one of the best places was in engineering, and I started my PhD in 1974, which is the same year that I got married to my husband, Tom. This is a picture of us, obviously, on our wedding day. So for those who've done the sums, you'll see that we've been married 40 years last year. And of course, we've hardly changed at all in that time. And this is a picture of us together at a dinner earlier this year. Yeah, there has been some change. Before I got my PhD, I actually got a research fellowship at Sydney Sussex College in Cambridge, which was a huge opportunity. This was 3 years of funding. Just really funding for me, not much funding for resources, but funding for me to do whatever research that I wanted to do. And that's a picture of Sydney. The first thing I did was finish my PhD, which I did the following year. And the title of the PhD was Acoustic Sources in Motion. This was the effect of these higher speeds that we were seeing, for example, on an aircraft like Concorde. And what my thesis was about was that higher speed actually changed the character of some of the sources, as well as just the overall level. And in addition, I worked on jet noise, and a particular aspect of jet noise, the noise of the jet is produced by turbulence, but in a high-speed jet, that noise is refracted as it propagates through the jet. And I was working on how one could model that. Now, when I got my PhD in 78, I had funding to do research, and the question was, what was I going to do research on? And Concorde then had been approved to land in the US, and I could have carried on in aircraft noise, but I actually found that the industry wasn't very interested in aircraft noise anymore. The particular target to get Concorde to be allowed to operate had been met. And it just wasn't a high priority for aviation in general at that time. So had I continued, I think it would have been a bit of a niche activity, and I was looking around for what else I could do. And one of the things that happened was the Ministry of Defence approached me, the technical people, And what I had done on how turbulence generated sound in a jet, a high-speed jet, and how its propagation was influenced by the character of the jet, they thought would be very relevant to them for the noise of submarines. Now, a submarine listens passively for distant sound in the ocean, which is the noise of other submarines. And as it does that, it's moving along. And all its sonar systems have flow over it because the submarine's moving. And that flow has turbulence in it. And the transducers that used to detect the weak incoming signals are actually sitting in a very noisy environment with turbulent flow over. And it's an environment where you've got the turbulent flow and you've got flexible surfaces, which is the hull, because even hulls and sonar systems are actually quite flexible underwater to low-frequency disturbances. So they asked if I would apply the kind of techniques I developed to jet noise to this underwater environment. And that led me into the whole issue of turbulence near flexible surfaces and compliant surfaces. And one of the things that I worked on quite early on was putting flexible coatings over sonar systems in order to attenuate some of the noise of the turbulence. And I did some theoretical work which showed it could be beneficial. And, you know, with a ministry project like that, you never really know. They just say, oh, yes, that's very interesting. It's very interesting. I think 15 years later, I served on a senior promotion board within what was probably by then not quite kinetic yet, but DERA. And the person that I was asked to review had taken that work and manufactured the complying coatings, and they've used them. So no one told me that at the time. But that led me into a whole load of other things relevant to water, like how can you use flexible surfaces to reduce the drag on hulls. And we know dolphins have very flexible skins. And it was learning from nature of the kind of compliance that could do things like attenuate the onset of turbulence, or if the flow was turbulent, would it be possible to reduce the drag? So this got me into all sorts of problems in underwater acoustics, and one of them I'm shown here. This was some work I did at the request of Schlumberger, so part of the oil industry. Schlumberger help oil producers find oil-bearing rocks. And it's done by towing what they call acoustic streamers, which are long aerials, and these can be up to 2 kilometers in length behind a ship. And in this long streamer, they would be full of hydrophones listening to the noise, and then they have a source, and they listen to the reflected waves coming back from the rock. And from that, you can determine the speed of sound in the rock and identify where you've got the kind of changes in structure that would mean that oil would be trapped at that location. But as they tow these hydrophones, there's a turbulent flow over them, and it can be, they're listening for these weak reflected sounds, turbulence on top, and the question is, how can one attenuate that? And it turned out again that you can make fancy layers of the right kind of compliant material in there to attenuate that so-called flow noise. One of the things Schlumberger wanted to do was to go from that sort of diameter aerial, which would be filled with liquid, to much smaller diameter, so that it'd be easier to deploy and have a viscoelastic interior. And I developed techniques which they used to design those so-called dry streamers rather than the liquid-filled ones. And it turned out to give them quite a niche in the marketplace, and meant in the end that with those small diameters, instead of towing a single one as shown here, you can actually have ships towing about 10 or more streamers at once and getting much more information. Another element that was back to aircraft noise was looking at the noise inside the aircraft, because when you're sitting inside, I don't know if you've noticed, it's much more noisy down the back than in the first class seats up the front. And that's because the turbulent boundary layer is growing as you go down the aircraft. And so you've got this unsteady flow, as it were, banging on the walls of the aircraft. And the lower noise that James referred to, unless, of course, you were sitting up the front in first class. But down the back, the lower noise is because you put sensible things on the walls that stop that transmission. So actually, it's very similar to the sonar problems. Turbulence on the outside, what's the right coating and what noise would you get inside? And a particular element of the fuselage is, for structural reasons, it's got lots of ribs. So as the turbulence excites the walls, there's lots of scattering that happens on the structural reinforcements, which made that a particularly interesting project. And then led me into my next noise one, which was, well, if you can do the stringers and ribs that support the aircraft structure, you ought to be able to do the patterns, the tread blocks on a tyre. And that, again, much of what I've done has been influenced by industry coming and saying, so in this case, it was Dunlop, and at that time what was Rover and then became JLR. They said, if you're either outside or inside and the car's going above about 30 miles an hour, the dominant noise is from the noise of the tyres in contact with the road. And currently, the design of the tread pattern on the tyre is done by the design department. And I don't mean mechanical design. This is the aesthetics of something that looks like it's a tyre that would go fast and looks modern. So it's purely, then it was being done on what it looked like. And so there'd be nice sweepy things. Now they had techniques that could predict how effective different patterns were at shifting water, but they couldn't predict the noise level effectively from different patterns. So that was the question. Can you help us do that? Lovely question to be asked. And that led into a whole series of work. And one of the things that's really important there is those tread blocks vibrate in a contact patch where the tyre's shaped like that and the road's underneath. And just the shape of that geometry gives a huge amplification. It's the equivalent of having something vibrating in free space or putting it in a trumpet where you've got a horn to match the impedances. So easily one got 20 dB amplification through that horn effect. And we dealt not only with the vibration, but how one could get a more leaky horn and avoid some of that amplification. But another area that was an important influence on my life, I'd been in Cambridge throughout. I wanted to get some industrial experience, and I went and worked in Rolls-Royce. And again, it wasn't for very long. It was just for 3 months. And I went and worked in the combustion department, so doing something completely different, and they gave me a job to do, and I designed how one could optimize a sampling to get the most representative sample from the exhaust of a jet engine. But as I was leaving, the head of combustion said, well, you've learnt about combustion now, you've been with us. I know you've got a PhD in acoustics. For decades, we've had this problem, which is the interaction between combustion and acoustics. It's been with us for decades. We know it's going to be with us in the future. Could you just go away and think about it and tell us what you would like to do about it? Is there something you can do to understand and get rid of it? So a lovely invitation. And I did think I could improve the modelling of it. But really, one would want to do a very controlled experiment to test out some of those ideas. So they said, right, well, write down what you would do. And I wrote down, I think, one side of A4. And they came back and said, well, you know, we are talking money for a large rig here. It's going to cost, and it was a lot in those days. And I was also asking for 3 years postdoc and a student. But the rig was the really big amount of money. And they said, well, a page isn't quite enough for us to commit to that. Could you make it 2? And that set up a rig that became a really important part of a very flexible rig that allowed me to do lots of things around combustion. This is a picture. It's not a very good picture, but this is one of the geometries we looked at. So what's at the heart of these instabilities is that you have combustion, and it's in a combustion chamber, which just tends to be a resonator, really. And when you perturb the combustion, the unsteady combustion generates sound. If you at home and the gas boiler comes on, when it first goes on, it roars. So when the combustion's really unsteady, it generates sound. But if you're in a resonant system like this, those sound waves bounce about and get reflected from the ends. And then you've got flow unsteadiness coming back onto the combustion. And the combustion can respond to that. So you've got combustion generating sound, but you've got sound producing unsteady combustion. And so you've got a feedback circuit that can go unstable. And that was at the heart of this instability. The first geometry I looked at was one for an afterburner on a jet engine. And so this is the main engine. This is the fan, compressor, combustion chambers, and turbine. If you just want thrust for a short time, and so, for example, Concorde used afterburners to take off and also to go transonic, where it needed thrust for short duration but didn't want to carry a bigger engine around all the time, you can do afterburning, which is really just squirting some more fuel in and burning it in an empty duct. And the idea there is you've got a particular mass flow. If you reduce the density by heating, you increase the velocity, but the thrust depends on the velocity squared times the density, and that increases, so you get more thrust. Now, these can go unstable for just that reason I've been describing. The flame is just burning in the wake of a body, so that's a bluff body, or a body that has a big wake behind it. The fuel gets squirted in upstream, and the flame just burns down there. And when you, small unsteadiness causing unsteady combustion, waves come back, they reflect, and that perturbation in velocity past this flame holder actually perturbs the flames, and you can see the wrinkles traveling down the flame. And that leads to unsteady combustion, the thing can self-excite, and it did self-excite in one Rolls-Royce engine known as the RB199. The frequency at which it self-excites depends on the time for acoustic waves to propagate up and down here and come back. And in this case, gosh, I've forgotten it so long ago, I think it was about 90 hertz, but it was very close to the main shaft frequency. So this was the torsional frequency, the shaft that goes between the turbine and the fan. So they had the potential of bigger pressure oscillations going up and down here, banging on the turbine at just a frequency that it would like to twist at. And they had one scary case where usually they would test an engine on the ground, and then they would also, when that was all checked out nicely, they'd then fly it and do a flight test. And in a restless night, the test engineer realized that the next day they were due to fly an aircraft at a condition that they hadn't yet tested on the ground. So he got everyone in early in the morning to do the ground test, and it did self-excite, and the shaft oscillated so violently that after they shut everything down as quickly as they could, it had a residual twist of 60 degrees in it. So the flight test was delayed. So this was a sort of an ongoing problem. I did modeling about what was going on. But one of the fun things was, could we actually control it? And anti-sound was a big thing around then. And so the idea was, well, we know what's causing it. Supposing we put the fuel in unsteadily, but with just the right phase, that it would burn unsteadily, but in out of phase with the way the flow perturbations were going to cause the unsteady combustion. So by adding some additional fuel, could we stabilize the system? Well, to work out what the phase was, one had to measure the pressure, have some sensible feedback, and then something to modulate the fuel. So we did work in the lab on our system, which was really a model of one of these flames, and it worked fine in the lab. Now, usually, the lab scale was like that, But that was about 1/3 of a megawatt. Normally, you'd go up through TRL levels trying increasingly complex systems. And Rolls-Royce said, nah, we may as well go straight to the engine. The lab results look good. We're going to do it on the engine next. So this is their experiment. And here is, with control on, very little pressure oscillations. Then they switched the controller off, and the pressure oscillations really grew rapidly. And then they had a monitor on this shaft, and when the shaft got too distressed because of the twisting going on, it cut the fuel out, and eventually that cut out there. So that was a really nice application that went right from lab to an engine. The only downside is once you understand a system well enough to design a controller like that for it, you actually know much easier ways of getting rid of the oscillation. And we could control it with passive systems that just increase the acoustic damping. And that's more what has happened in practice. But research carried on the active control, and one of the things that really wanted to do, of course, if you operate an engine, you go through lots of different operating conditions. And so you really need a controller that can learn online what it needs to do in an adaptive system. And I worked on adaptive controllers with a colleague at MIT, where you put some structure into the feedback control, which was based on an understanding of the kind of response that you got from the combustion system, but not any details about frequencies or numbers, but just some very simple assumptions about the response, that it didn't respond at very high frequencies, for example, things like that. And then online, the feedback system learns what parameters are needed in the controller. And this is an example on the rig. These are the pressure oscillations. And then the controller switched on with all its parameters set to 0, so it doesn't put any fuel in initially. And then it starts to put some more small amounts of fuel in, valve openings, the unsteady fuel going in, learns online what the parameters in the controller need to be. There were a lot of them. I've just shown one here. And then it finds a converged solution, brings things under control, and the pressure comes right down, with the valve working less hard, and then when we switched off the controller, the sound grew. So that sort of took me from knowing about acoustics to learning about, well, through linear systems, which is just what acoustics is, getting into control, getting into robust control, model-based control, and adaptive control. The combustion activities at Cambridge were really growing, so I was looking at a range of things, and Rolls-Royce, who'd always been funding turbo machinery work there, wanted to grow our partnership to include not just turbo machinery, but also combustion and acoustics, and we set up something called the University Gas Turbine Partnership, which I then ran. And aviation's always been important. It's been a hobby as well as part of my career, and here's me in a sort of 1980s hairstyle flying. I had a share of an aircraft and going out for the day, because Cambridge is far from the coast or mountains, so the aircraft is a good way of going out. I became a reader in '86, professor in '94, and something that made a big change was a sabbatical at MIT around about the millennium. I became a fellow of the Royal Society in '97 and vice president not very long afterwards. I think they were really keen to have a woman vice president who didn't have many duties associated with it. At MIT, we'd have these bag lunches where we'd talk about, I was visiting the aero department, what would really make a difference to aerospace. And aerospace is really constrained by the fact that airports at locations where people want to fly from are operating at full capacity. No one wants an extra runway or an extra airport anywhere near where they live. And we thought just making an aircraft a bit quieter wouldn't be enough, but supposing we could come up with a silent aircraft. And then we'd start to talk, well, what would it look like? What would it have to do? And so we'd been talking about this. And it was sort of for fun, but we thought it was a really important area to look at. So I began to get interested in applying my acoustics knowledge to aircraft noise again, rather than instability and underwater. So that led to the Silent Aircraft Initiative. This is, I've got a few slides now on that work. Now this is a plot of aircraft noise plotted against year of entry into service, suitably taking into account of the weight of the aircraft. And you can see that aircraft noise has really decreased since the introduction of high-speed jets. The noise has gone down by some 20 dB. The other thing, though, is that the rate of change of decrease of noise with time has almost leveled off. It's getting much harder to reduce the noise further. And the early reductions were due to, the early noise was all due to jet noise, the noise of the high-speed jet coming out the back, and the sound increases hugely as the speed, Mach number of that jet increases. So the big wins were going to a bypass engine, where instead of getting the thrust from a single jet moving at very high speed, you get the thrust that you need from moving more air more slowly by having a big fan around the engine. So the high-speed jet drives a turbine, and the turbine drives a big fan that you see at the front of modern aircraft. So you get the thrust you need by having a bigger mass flow rate of air with a smaller velocity. That brings huge benefits for noise. It also brings reductions in fuel burn, and this is fuel burn per passenger mile. But again, what has happened now is the big fan at the front makes as much noise as the jet. And so if you just go to further increases in bypass ratio, you increase the noise because the fan becomes even more noisy. And you also increase the drag because those big fans have lots of drag on them. So the wins, whereby increasing the bypass ratio, reduced noise and improved fuel burn, have pretty much been cashed in. So to be so-called silent, well, obviously it's not going to be completely silent, we set a target that if you were outside the airfield perimeter, the noise of a landing or taking off aircraft should be no louder than the background noise in an urban environment. So if you were in the countryside at night, you would still hear it, but in an urban environment, daytime, you shouldn't hear it. So funny definition of silent, but that's where we ended up with. And it leads to this level here, which is about the same reduction from current aircraft as current aircraft are from the high-speed jets introduced in the mid-1950s. And it actually means reducing the acoustic energy to about 0.3% of the current energy levels in an aircraft. So if we didn't make any preconceptions about what the aircraft should look like, could one design a mid-range passenger aircraft that would reach that noise level outside the airport perimeter? And if we could, what would be its fuel burn? Now, we got money from an initiative called the Cambridge-MIT initiative from CMI. Extraordinary, really, to get money to do that sort of thing. It's not something many funding agencies would fund, but we were very pleased. And I think in total we had about 40 researchers from Cambridge and MIT working on it. But you can't just have academics and students and postdocs designing an aircraft. Industry involvement was absolutely crucial here. And we had something like 25 industrial partners, but the main ones were Boeing, who made some of their design codes for blended wing bodies available. Rolls-Royce, again, let us use their engine design codes. Some of our parameters went outside their range, and then we developed the codes, and we also did some experiments to test as we went beyond. We brought in a local aerospace company, Marshalls. We had advice from NASA. The regulators, NATS and CAA, were partners. And we had a number of airline and airport operators involved. Hackana were fun. They're the Heathrow active campaign against noise. They liked what we were doing. And then we had equipment manufacturing. And Cranfield University did a small-scale alternative study, but using some of the same codes that we were developing. Noise sources on conventional aircraft. So at takeoff, the main noise comes from the engines, from the fans, the big fans at the front. The fan inlet noise is attenuated by having acoustic liners, sound-absorbent material around the intake ducts. But you also get the noise of the fan propagating backwards out through the bypass ducts, and that's pretty much the dominant noise source. And as I was saying earlier, almost equally balanced with the noise from the turbulence in the jet. On landing, the airframe makes almost as much noise as the engine, and the airframe noise comes from the undercarriage. It comes from the flaps, which are lowered to increase the drag, and from the slats, which are lowered to give high lift. Not much jet noise then, but the fan is operating off design, and you get a large amount of forward propagating fan noise. Our target level is this dashed line here, so we had to address all those noise sources. This is the design that we came up with, and I won't have time to go through all the details. It's what's known as a blended wing body, which means you get lift on the center body where the passengers sit, as well as on the wings. We came up with a design with 3 engines, and they are embedded in the airframe, and each engine has something that's like a conventional engine with a fan, compressor, turbine. But that turbine drives not just its own fan, but 2 auxiliary fans. And this way we get lots of low-moving air from one single core. And that's what is in one of these compartments here. So in total, we've got 3 of those and 9 fans in all. So in this way, we're able to get that high bypass ratio by having lots of air moving slowly. But because the fans sit side by side and each of them hasn't got a particularly high diameter, we're able to embed them in the airframe in a way that doesn't increase the drag very much. We estimated the fuel burn to be about 25% better than current aircraft, and also that we would meet our noise target. These are some 4 directional views, and from on top and the side it looks, well, that direction looks quite elegant. Side on it looks really ugly. And it's been described as looking like a pregnant cow from this direction. But we referred to this as undercarving or a chin, but actually this was the secret of some of the good aerodynamic performance. An issue with the reason for the chin is an issue with blended wing bodies is actually getting a nose-up moment that you can then trim about for flight. Now, Boeing have a blended wing body design, but the design they had at that time got that nose-up moment by having some downward force here towards the back of the center body. Now, if you're designing an aircraft, you don't want to have a downward force. Okay, it gives you the right moment to bring the nose up, but that downward force really is destroying lift, which is the ultimate aim. But that carving that we had, it produces an upward force near the nose. And so you get that upward moment by having the aerodynamic shape giving some upward force near the nose rather than downward force at the back. Now, we were doing a fairly quick, simple methods to predict the aerodynamics. And through that, we were able to do lots and lots of cases and lots of optimization. And once you get the center body giving this pitch up moment, then you can really optimize the outer wings. And in doing that outer wing optimization, it was possible, we came up with shapes that look very much like the shapes of modern aircraft. They weren't compromised in the way other blended wing bodies are. And the lift distribution on the outer wing was an elliptical lift distribution. I know there are a few people in aerodynamics in the room, so this is the holy grail for aerodynamics. It's the best kind of lift distribution you can have to maximize lift to drag. Now, as I said, we were using fairly simple approximate methods to do this, and it has to be said that Boeing, who had already got their own blended wing body design and had been flying a scaled model of it, didn't believe the figures we were getting for lift to drag on this because it was so much better than their blended wing body. So they said, could we take your geometry? We let them take the CAD files, and they ran it on their own in-house CFD. It's rumored the lights dipped over Seattle as they crunched away at this for several months. And they came up with their solution, which actually confirmed, I've got something blocking there, but it actually confirmed the lift properties that we were predicting. And since then, Boeing have got, well, I'll say a little bit more. Boeing has got NASA to go on and develop more on this geometry for them. So the things that lead to low noise, with those 3 fans in each engine, 9 fans in all, we're able to get a high bypass ratio, which reduces the jet noise. The jets are so low speed, they wouldn't give good efficiency in cruise. So we've actually got nozzles that would close so that in cruise you can close the nozzles down and get a high-speed jet, but have a low-speed jet near the ground. The airframe is an important element to reducing noise because the fans here will produce noise, but it's prevented from reaching the ground because the engines are mounted on top of the airframe. And also there's sound-absorbent material fore and aft of the engines. So this little movie, which is from models in a water tank, just illustrates some of the shielding effects. A conventional aircraft has the engines underneath, so such interaction there is with the aircraft. Worked earlier. Such interaction there is with the aircraft tends to reflect the sound downwards. Whereas if you put the engines on top, I think you can imagine how it goes, that the sound goes up. I don't know why it's misbehaving. Just try once more. No, it's not going to do it. No. The engine's on top, the sound goes up. I've got some sound files, which I hope will work, and these are our predictions of the noise. When the engine team first started to design the engines for this, using Rolls-Royce's codes, they said, well, I want to see that, you can design a normal engine. So they were given a task which was equivalent to one of the engines that Rolls-Royce had in planning at that stage. So the team designed it, and it was a blind study, but it turned out to look very similar to the Rolls-Royce design. And what you'll hear is, first of all, the noise from that so-called conventional design. Then they did various things to minimize the noise from the turbo machinery as much as possible. So you'll hear the noise from that. And then this first case is the noise behind the aircraft and at 40 degrees down from the horizontal. So the effective shielding is negligible there because there's no there's no blocking surface. But the rearward duct passages are lined with sound-absorbent material. So next you hear the effect of the liners, and then you'll hear shielding plus liners. conventional. So this is design reduction, no effective shielding, and then the liners, which you can just hear. So that was behind, and now this is the engine noise down and in front, where now shielding will have an effect. Conventional. Spare engine. Shielding. Liners. And shielding plus liners. So really big attenuations from the shielding and from the liners. And we gave ourselves longer ducts than you would have in current designs, but that's possible because of the shape of our geometry. Moving on with the technologies for low noise. The airframe design with that high lift to drag ratio actually has a lower stall speed. So we would propose to bring this aircraft in a bit slower than normal, and many of the airframe noise sources scale on velocity to the 6th power. So coming in slower, just a bit slower, still within the standard pattern of traffic around an airport, but slower than a normal aircraft of this size would be. I'm not sure if I said, it's supposed to take 250 passengers. Operations are therefore important. And at takeoff and climb, we would optimize the thrust and indeed the thrust for minimum noise on the ground. And a slightly slower, slightly steeper approach. And there's a double benefit from coming in slightly slower. You can land further down the runway and still stop with all the required safety features. And actually, some airports are already doing that. For Frankfurt does it, has a displaced threshold for aircraft that are smaller or lighter or can, yeah. So it's not particularly new. Slats are noisy, and we could get the additional lift that we needed with just a continuous drooped leading edge. This is something that's used already on the A380. The undercarriage, we designed fairings for to reduce the noise. This is showing some of the airframe noise sources, the engines, but also the undercarriage. And I've got a few slides on the undercarriage noise, which I don't think I'll have time to do, but this just illustrates the kind of things that we were doing. Each of these noise sources would have a couple of students, PhD students, student and postdoc working on. We were making noise measurements with a phased array of microphones, 96 microphones, pinpointing where the sources of noise are. And the real source of noise is the wake of an upstream pair of, upstream wheel impinging on the downstream wheel. So we did things to reduce that, like really controlling the separation points upstream and staggering the wheels a bit so that the impingement points were not at the edges of the downstream wheel. That's really the main message. I'm going to skip this, but that gave about 7 dB reduction. And this is just the intensity plots with those changes on, and some fairings on the wheel, struts holding the wheel. So I haven't got time to go through the details, but each element of this modeling did have wind tunnel or more detailed models behind them. This was also good for low fuel burn. The high bypass ratio engines are good for low fuel burn. The variable area nozzle meant we could, even within cruise, continue to operate at peak efficiency even as the weight of the aircraft changed, whereas a normal aircraft, you have a fixed nozzle and you can't operate at peak efficiency all the time. The low drag airframe also helped reduce fuel burn. By embedding the engines like this, we were able to reduce the drag. And this is just showing the noise level of this aircraft at takeoff, sideline, and approach compared to the noise of the existing fleet. And it is some 25 dB quieter at each condition. The cumulative EPNDB is adding up the reductions from the 3 conditions. So we met the noise target. And it wasn't a single technology that was the answer, but really the way in which they were integrated into an aircraft with into an aircraft and operated differently. We also worked on something we called a low-risk version. The highest risk really was embedding the engines in the airframe. They have a distorted flow going on to them. We also worked on something we called the low-risk version, which had podded engines. And NASA picked up on that one, and they've built a scale model and have now done some aerodynamic, because one of the real bits that's hard to model is what's the low-speed, high-incidence aerodynamics like. So they've been doing wind tunnel tests on that, and they've also done aeroacoustic tests on the wind tunnel model. They're still analysing the data, but it's looking very encouraging. And for me, this was getting me back into aircraft noise again, because it showed that some of the fundamental noise sources, jet noise in particular, needed better models. One was needed to be reduced even for current aircraft, and that got me back into thinking again about aircraft noise. And I'm working on various noise sources now, in particular explaining why these edges at the back of aircraft, which are currently developed quite empirically, why they're good to reduce noise. And it's all to do with, they generate streamwise vorticity, which alters the mixing. And we now have models that can explain in which ways these alter the mixing and the noise sources. Going back to my life, I got a CBE. That was a picture of me with the Queen. I had another sabbatical at Caltech, which was around control and combustion. And alongside my main academic career, I've always been involved in a number of policy or governance of science. So I've been on various committees like EPSRC Council. Following on from that, I became head of our energy division, and then subsequently head of the engineering department in Cambridge, and other external things that I've done recently, for example, chair of main panel B. I'm currently a non-exec at BP, and also our government departments have non-execs, not proper directors, because after all the ministers are in charge and have been voted to be in charge, but external people who give advice. And I'm on the board of the Department of Business Innovation and Skills, which is where research gets funded. Obviously, business gets supported, but research gets funded in universities. I was really pleased to get an honorary degree from Imperial College, and here's a picture of me on your fire engine a couple of years ago. And then last year, as you heard, I became president of the Royal Academy of Engineering, and that's been the quick canter through that I plan to give. I think that was my last slide. So thank you very much.
And I think the prolonged applause says it all, really. I'm awfully sorry about the fire engine, by the way.
Oh, it's great fun.
Oh, good.
I got to ring the bell.
OK, fine. As long as you got to ring the bell. We do some dreadful things to people we give honorary degrees to, don't we? So I feel embarrassed now. James said at the beginning you were a role model, and your lecture has been fantastic, and your career has been amazing, and you are the most amazing role model. This is where we celebrate our women in STEM. And it's hard to think of somebody who could help us celebrate it better than you have today. But let me ask you a question. You've all, in the 1970s, I also remember the 1970s, there were very few women in engineering. Was it ever an issue for you that you must have been a bit alone? There can't have been many other women around in engineering at that time.
I
Did it ever
didn't feel
matter?
alone.
Oh, yeah.
So in maths, there
Yeah.
were more. There were other women. I mean, I remember, tea breaks and things. There were other women around, so it didn't really feel. It didn't feel odd, actually.
Good. In that case, you need to tell that to lots more women, because we still have a shortage of women in engineering, though why they should when you've had your fantastic career and worked on all those amazing problems. We don't probably really have time for questions, but if there's somebody in the audience got a technical question, you can ask it now. Anybody busting to ask something? Yes.
In terms of looking forward to the future, the use of domestic drones, prepared Amazon, Facebook, looking forward to using drones for commercial deliveries and being internet. Do you sense that as being the next future of some of these problems? Because like some of these drones, buffeting of the fans that they generate. Do you sense that as a next future of the research?
So one area that I didn't quite catch all of that, but one area that I am
drones.
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 Oh, drones.
Yeah, yes.
Oh, drones. Right. I think we will certainly see drones be used for all sorts of applications already, for things like pipeline inspection in remote areas. They're very popular. Of course, you don't want them mixed up with civil aerospace, and I think there's a whole issue around regulation that really is quite challenging. As someone that's flown a small aircraft, where yes, you do sometimes fly in controlled airspace where your clearance is guaranteed by ground radar, but sometimes you're outside control airspace and it's see and be seen. But drones are so small that you might not see them, but they could still do a tremendous amount of damage. So, real segregation on heights would be really, really important there if they become widespread.
All right, one more question at the back.
Have you looked at active noise cancellation?
When I talked about that control of the instability by putting the fuel in, the way we talked about that, first of all, was very much in terms of anti-sound. And the very first controller was as simple as, I'm detecting a pressure, what do I need to do to produce a pressure wave out of that? But really, for us, it was an instability issue, and it became much more sensible to think about it in standard control terms. So I've not done actually anti-sound, although it was a strong influence in the early thinking on that. Most of what I have worked on other problems that where the pressure wave has been reduced in one way, but it's really been more in issues where there are instabilities present. So the quick answer is no.
All right, I think we have to draw this wonderful lecture and event to a close. Thank you all for coming, but most especially, Anne, thank you for the most wonderful and inspiring lecture and for being such a wonderful role model. Thank you so much. And if the fire engine wasn't enough, there's some flowers. I hope you're staying in London tonight.
I am, that's lovely. Thank you.
Thank you so much. Thank you, everyone.
Thank you. Fantastic. Sorry, I